In the next problem, we are to determine the DFT of the signal x of n, which is equal to a to the power n u of n, where n goes from 0 till n minus 1. So let us say we know from the direct transform equation x of k, which is equal to n which goes from 0 to n minus 1, x of n e to the power minus j twice pi kn over n, and now since u of n, that is the unit step function, is equal to 1 for all values of n greater than or equal to 0, then from the range 0 to n minus 1 it will also be equal to 1. So we can simply write x of k is equal to n which goes from 0 to capital N minus 1, a to the power of n, and since u of n is 1, we need not write it, e to the power minus j twice by kn over capital N. So now bringing this small n term out of these two expressions and as a raised power, we can write n which goes from 0 to capital N minus 1, a e to the power minus j twice by kn raised to the power of n, which is obviously in the form summation m to the power of n, where n goes from 0 to n minus 1, and this has a value of m to the power of n minus 1, m minus 1, otherwise 1 minus. So any one of them you can use. I'll be using the second one. So simply we can write x of k to be equal to 1 minus a to the power of n, replacing n with capital N, e to the power minus j twice by k capital N by n, whole divided by 1 minus a e to the power minus j twice by k over n. This is equal to 1 minus n cancelled, a to the power n e to the power minus j twice by k, 1 minus a e to the power minus j twice by k over n. So as we have seen this term many a times before, this will be always equal to 0. So finally we get the transformed equation to be equal to 1 minus a raised to the power of n whole divided by 1 minus a times e to the power minus j twice by k over n, and this is our required discrete Fourier transform. So this was the problem, and let us move on to our last problem on DFT. Okay, now here it is said example 4, compute the 4-point DFT of x of n, where x of n is 0, 1, 2, 3, using the Twiddle factor and also verify the result by means of the IDFT, that is the inverse discrete Fourier transformation relation. So let us go to the solution. So we know Wn to the power of Kn is equal to e to the power minus j twice pi Kn over n. So we need to find out the values of W4 to the power of 1, because before that let us find out W4 to the power of 0, where n is 4 because our signal has a length of 4, since there are 4 values, and 0 being the multiplication, the product of k times n. So W4 to the power of 0 is e to the power of minus j twice pi. Instead of Kn we write 0 whole divided by 0. This entire expression becomes 0 and e to the power 0 will become 1. So now similarly we find out W4 to the power of 1, e to the power of minus j twice pi. The k times n term becomes 1 over capital N, which is equal to e to the power minus j pi by 2, because n over here is 4 and 4 divided by 2 becomes 2. So we can cancel the numerator and denominator with 2 and we are left with pi by 2. So this can be expanded using the Euler's relation, cos pi by 2 minus j sine pi by 2, which is equal to negative j, because cos pi by 2 is 0 and sin pi by 2 is 1. Fair enough. So we find out for W4 to the 2, e to the power minus j twice pi times 2 whole to the power of n, which gives us e to the power of minus j pi, and expanding using the Euler's relation we get cosine of pi minus j sine of pi, and this value cosine of pi, it is negative of 1 and sine of pi is obviously 0. So the result is 1. I mean negative of 1, since this is negative of 1. Very well, we find out W4 to the power of 3 e to the power of minus j twice pi 3 over n e to the power, which equals e to the power minus j thrice pi over 2. This can be written as cosine of thrice pi over 2 minus j sine of thrice pi over 2, and cosine of thrice pi over 2 is equal to 0 and sine of thrice pi over 2 is equal to negative 1. So this negative and negative becomes positive. 1 times j becomes j. Very well, we go to our final value, w4 to the 4, we get e to the power minus j twice by 4 whole to the 4 divided by 4, I mean. This gives us e to the power minus j twice pi cosine of twice pi minus j sine of twice pi. So cosine of twice pi is 1 and j sine of twice pi is 0. So this becomes 1. So simply speaking, we can define all this value in the circular domain. So these are our 4 equidistant parts. If this is w4 to the 0, this is w4 to the 1, and this is w4 to the 2, and this is w4 to the power of 3. We write down the value as this to be 1, w4 to the 0 is 1, w4 to the 1 is minus j, w4 to the 1 is equal to minus j, w4 to the 2 is equal to minus 1, and w4 to the 3 is equal to plus j, and w4 to the 4 is equal to 1 again. Similarly, w4 to the 5 will be equal to minus j, w4 to the 6 will be equal to minus 1, and it will go in this direction. Simply because, say for w4 to the power of 5 can be written as w4 to the 4 times w4 to the 1, and w4 to the 1 is having a value of j, so it is negative j. So we can see that the value of w4 to the power of kn will be periodic, and it will repeat itself along the circumference of this circle. Now, if that is the case, let us construct the Twiddle matrix. So our Twiddle matrix which is w4 in bold letters, where the first value will be w4 0 times 0. Now we are taking k equals to 0, k equals to 1, k equals to 2, and k equals to 3. In this direction, n equals to 0, n equals to 1, n equals to 2, and n equals to 3 in the columnar direction. So here w4, k is 0, n is also 0, so 0 times 0. Here it will be w4, k is 0, n is 1, so 0 times 1. Here it will be w4, 1 times 0. And similar fashion, let us fill up the matrix. This will be w4, 0 times 2, w4, 0 times 3, w4, 1 times 1, w4, 1 times 2, w4, 1 times 3, w4, 2 times 0, w4, 2 times 2, I mean 2 times 1, w4, 2 times 2, w4, 2 times 3, w4, 3 times 0, w4, 3 times 1, 3 times 3, and w4, 3 times, this will be 3 times 2, and this 3 times 3. So this is the basic form of our Twiddle matrix. Now simply we multiply the indices and we can write this to be equal to W4 to the 0, 0 times 1, W4 to the 0, W4 to the 0, W4 to the 0. And this value of W4 to the 0 will be same to the 0 as n over in this direction is 0. This will be W4 to the 1, W4 to the 2, W4 to the 3, W4 to the 2, W4 to the 4, and W4 to the 6, W4 to the 3, W4 to the 6, and finally W4 to the 9. Now finally we can write W4 to be equal to, just putting the values from here, W4 to the 0 is 1, so all this value will become 1, and in this direction it will also become 1. Fair enough. Now W4 to the 1 is equal to minus j, so W4 to the 1 is equal to minus j. W4 to the 2 is equal to negative 1, so we get W4 to the 2 here and here, so this will be negative 1, this will also be negative 1. W4 to the 3 is j, so we get W4 to the 3 over here and over here, so this will be j and this will be j, I mean plus j and plus j. W4 to the 4 we have found out to be equal to 1, so this will be 1. W4 to the 6, so this is W4 to the 0, 1, 2, 3, 4, 5, 6 will be equivalent to W4 to the power of 2, which is negative of 1. This is negative of 1, and W6 also occurs over here. This will also be negative of 1. Similarly, W4 to the 9, this is W4 to the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it will be having a corresponding value of W4 to the power of 1, which is negative of j. So this is our required 4 by 4 Twiddle matrix. Now in order to find out the DFT, simply what we need to do is just assume a columnar vector x of 0, x of 1, x of 2, x of 3, multiply our Twiddle matrix 1, 1, 1, 1, 1, 1, 1. This becomes negative j minus 1 positive j, becomes minus 1, 1, and minus 1 again. This becomes positive j minus 1 and negative j. This is to be multiplied by x of 0, which is equal to 0, x of 1, which is equal to 1, x of 2, which is equal to 2, and x of 3, which is equal to 3. Now, life would have been very much easier if these two matrices were not complex valued. If this were real valued matrix, we can simply plug in the values in the calculator and it would have spit out the answers. But this is not the case, so we need to calculate it manually. So, I hope all of us know how does matrix multiplication works. So it becomes, the first row is 0 times 1 is 0, 1 times 1 is 1, 2 times 1 is 2, 3 times 1 is 3. This is our first value. Similarly, we get 0 times 1 is 0, 1 times negative j is negative j, 1 times negative 1, sorry, there seems to be a mistake. 0 times 1 is 0, 1 times negative j is negative j, 2 times negative 1 is negative 2, and 3 times j is plus thrice j. This is our second value. So 1 times 0 is 0, negative 1 times negative 1 times 1 is 1, 1 times 2 is positive 2, negative 1 times 3 is negative 3. And finally 1 times 0 is 0, plus j times 1 is plus j, minus 1 times 2 is minus 2, and minus j times 3 is minus 3j. So let us add up these values. We get 6 minus 2 plus 2j minus 2 minus 2 minus 2j. So these are our value of the required discrete Fourier transform, this being capital X of 0, capital X of 1, capital X of 2, and capital X of 3. So now we are also said to verify this result using the IDFT relationship. So now for IDFT, we know that W inverse 4 is equal to 1 over n times W conjugate of 4, which is equal to 1 over 4 since n being 4, and W conjugate matrix is, this will be 1, 1, 1, 1, 1, 1, 1. Simply just changing the sign of all the negative, all the imaginary numbers. So this will be becoming plus j, minus 1 doesn't have any imaginary part, it will remain as it is, this becomes negative j. And similarly, let us fill it up. This is our W4 inverse of 1. So why did we make W4 inverse 1? This is because if this W4 inverse 1 is multiplied with our capital X of k vector, then we will get back our X of n vector. For more clarification, I suggest that you refer to the video that I've done on linear transformation of DFT. So solving the matrix, in order to get X of 0, X of 1, X of 2, X of 3, which is equal to 1 over 4, 1, 1, 1, 1, 1 plus j minus 1 minus j, 1 minus 1, 1 minus 1, 1 minus j minus 1 plus j. This is our inverse Twiddle factor, and we are to multiply it with 6, 2 minus 2j minus 2 minus 2 minus 2j. Now similarly, once again you can matrix multiply it. This will give us the value 6 minus 2 plus 2j. You can multiply and verify the results. Minus 2j 2 plus 2j minus 2 plus 2 minus 2j minus 2 plus 2 plus 2j plus 2j plus 2 plus 2j plus 2. There is a 1 by 4. So this becomes 1 by 4, 0, 4, 8. All this imaginary term will cancel each other out and we will be left with the real terms. Now multiplying this vector with the scalar factor 1 over 4, we get our required x of n. Let me write it, squeeze it over here. 0 over 1 by 4. 0 times 1 by 4 is 0. 4 times 1 by 4 is 1. 8 times 1 by 4 is 2. And 12 times 1 by 4 is 3. So this was our required x of n as shown in the question over here. So the result was hence verified. So with that, we come to the end of our discussion on DFT. In the next lecture, we shall be concentrating upon fast Fourier transform. So on that note, let us conclude this part, and I hope you will remain safe, and goodbye.